Thank you very much for the invitation to this conference, and many thanks to the organizer for putting the conference together. So my talk would be somewhat low tech, but the title is Asymptotic Homotopy and K-theoretic Duality, and it is based on joint work with Terry Loring, one paper, and then Ulrich Penning, that's another paper, and then a paper with Willett and Zhang Chao Wu. And I will discuss three topics on the role of asymptotic homotopy, then asuspending in E-theory, and then I will revisit duality isomorphism between the KK theory groups and the K-theory group of localization algebra associated to the pair. And unlike the Paschke duality, there is no shift in dimension here. But the overarching theme of the talk would be a discussion of the role of asymptotic homotopy in K-theory. And this is what I will start with. So on the role of asymptotic homotopy. So in the talk, XY would be locally compact spaces, and it, as usually will denote by C0X, the system algebra of complex valued continuous functions vanishing at infinity. And then one can reinterpret Tietze's theorem, extension theorem, as giving an exact sequence of C-star algebra associated to the pair Yx, where Y is closed. And indeed, Tietze's theorem allows us to deduce that the quotient map, which is a restriction map, in this case, is surjective. So if we are to pass to C-star algebra notation, C0xy, that's the algebra of functions on X vanishing on Y, and that will correspond to the ideal J, and right, feeds a surjective map. And then, of course, just like for spaces, we have these very basic constructions. The cone of a C-star algebra, and I'm using here Kasparov's notation, B of the semi-open interval 0, 1. So it consists of continuous functions on the unity interval vanishing at 0, that's the cone, and then suspension function vanishing at both endpoints. And then the mapping cone of the star homomorphism phi. So this consists of pairs. The first component is a function in the cone, and then an element of A, and they satisfy this notation. And when I was a student and studied the first time C-star algebras, I saw suspension, but I was puzzled. In some sense, it had a feel that it's too commutative. I thought that for C-star algebras, being non-commutative algebras, these notions shouldn't be suitable. But yeah, that was the wrong feeling. But still, sometimes I wonder. As usually, we denote the homotopy classes of star homomorphisms by using these right brackets. So we view this as a pointed set where the point corresponds to the homotopy class of the zero homomorphism for now. Okay, and then as a first way to validate this construction mapping cone is this exact sequence of a pointed set, which the first time I read about it in a paper of Jonathan Rosenberg. So if one learns homotopy theory for the first time, might ask, what is the role of cone? What is the role of suspension? And this is one of my favorite explanations. So homotopy leads naturally to mapping cones. All right, so this is like a piece of the puppet sequence, but one thing we might not like it with an eye on computation is this term here, which involves the mapping cone, whereas we would much prefer to have the ideal over there. But unfortunately, or maybe fortunately, the sequence is not exact in general. And of course, this is a well-known phenomenon. So I'm indicating here that the mapping cone of a surjective map phi is not homotopy equivalent to the ideal. And indeed, for spaces, we know that if we attach a cone over a subspace Y of X, this is not going to, it's not in general homotopy equivalent to the quotient space X mod Y. Now, interesting enough, of course, if one wants to iterate this construction, so the mapping cone, so I read the definition, had two components, one in the cone and one in A. So one has a map which projects 2 onto A. I call it P. If one takes the mapping cone of P, then it turns out that this is homotopy equivalent. This is homotopy equivalent to the ideal. Okay, so but still we are left with the mapping cone there. And one way to understand the role of asymptotic homotopy is that if one replaces star homomorphisms by asymptotic homomorphisms and looks at the homotopy classes of such objects, then the mapping cone and the ideal, they become asymptotically homotopic, at least if we take suspensions. So let me review briefly the notion of asymptotic homomorphism. An asymptotic homomorphism from A to B consists of a family of maps, phi sub t from A to B, parameterized by the semi-interval. And for each element of A, the map T goes to phi sub t of A, which is an element of B, should be a continuous and bounded function. And this family of maps satisfies asymptotically the axioms of a star homomorphism. So they are asymptotically linear, asymptotically multiplicative, and asymptotically self-adjoint. And then, as was mentioned already in the conference, there is a natural notion of homotopy for such maps by using the cylinder. So if I have a C-star algebra B, continuous function from 0, 1 with values in B, of course, that it plays the role of a cylinder over B. And then we say that two asymptotic homomorphisms are homotopic if we find a homotopy in between them consisting of asymptotic homomorphism. So you can see here formalized the notion of homotopy, where capital phi is an asymptotic homomorphism. And I'm going to use, as traditionally, double brackets to denote homotopy classes of asymptotic homomorphisms. All right, so now with this weakened notion, more flexible notion of asymptotic homotopy, the mapping cone and the suspension become equivalent and ideal, they become equivalent. So therefore, by Puppe sequence, once we introduce these groups, which one may call asymptotic stable homotopy, stable in the sense that in the topological sense, we keep suspending and take a direct limit, and then we obtain a family of groups. And these groups now give rise to an excisive bivariant theory on separable sister algebra, which in general is not periodic. So of course, all this was is well understood, but in late 80s, it was unclear whether there is any excisive bivariant theory which is not periodic. So Kasparov's KK theory was the only bivariant theory known. And then, of course, Hickson constructed abstractly E-theory, which was later realized by Conan Hickson. So once again, so as I said, I make this very elementary. If one has an exact sequence of separable sister algebras, then by stabilizing using suspensions, we get long exact sequences in each variable. So this is, we might call it the stable asymptotic homotopy. And it's not periodic, but it has perfect excision. Of course, everything here is based on the crucial insight of Conan Hickson, the idea of asymptotic homomorphism. And E-theory was defined as homotopy classes of asymptotic homomorphisms, stable homotopy classes from A tensor K to B tensor K. But remember, in this definition, we take suspensions. Okay. In this context, then the Bott periodicity becomes this asymptotic homotopy between the first suspension of A, tensor the compacts, and the suspension of A. So they are asymptotically homotopic. And in this setup, one can obtain yet another distillation of Bott periodicity, which I wrote here as this asymptotic homotopy, but even more basic, what is behind the Bott periodicity. So we know that we have this canonical sequence, exact sequence, which involves the cone and the suspension, which of course is fundamental even for the complex numbers. And there is a dual object, namely the Toplitz's extension. So this is the extension which involves Toplitz's operators whose symbols are vanishing at a point. Okay, so the symbols therefore are in continuous functions on the circle vanishing at a point, so the suspension. Okay, and it turns out that the suspension of the Toplitz's operator tensor the compact operators is asymptotically homotopic to zero. Okay, so the way I like to view these two fundamental extensions is, in some sense, in topology, if you want to connect two spaces, sometimes that can be done having a vibration, maybe a set vibration, where the total space is contractible. And here we have a similar situation. The total space, the algebra in the middle, it's contractible because we have the cone, and in the second instance, it's contractible in a suitable sense because we have this Toplitz's operator. So one may perhaps exaggerate a little bit and say that Bott periodicity, it's exactly the existence of this Toplitz's extension. the Toplitz's extension itself by its mere existence, which is Bott periodicity. Okay, but I speculate. All right, so due to Bott periodicity, one can unsuspend in theory, but still we need to keep some suspension. And I wrote here representation of E-theory. So E0, homotopy classes of asymptotic homomorphism from the suspension of A tensor the complex to the suspension of B tensor the complex. Or one can use only one suspension, well, a double suspension in the first variable. And then in the same spirit, E1 is given by homotopy classes of asymptotic homomorphisms from the suspension of A to B tensor K. All right, what is the role of suspensions in E-theory? So first, we know that C-star algebras are in some sense very rigid objects. There are no maps, no star homomorphism typically between C-star algebras. And so, for instance, if A was Kunz algebra, purely infinite algebra, and B compact operators, we have no star homomorphism. So even if A, it's a C-star algebra which has no compact representation. So there are no maps. But on the other hand, if one introduces suspensions, that the suspension of an algebra tames the algebra, not only that introduces implicitly a group structure, but also makes the algebra quasi-diagonal. And we know that quasi-diagonal algebras are maps, are algebras which admit many asymptotic homomorphisms to matrices. So the suspension, the role of suspension is not only to bring a group structure or Bott periodicity in this instance, but also to assure that we have maps. There are lots of maps. One can think of these maps as deformations of A into B. Now, E-theory has perfect excision, and then we revisited why that is the case. So that was the asymptotic homotopy between the mapping cone and ideal. And then a lovely result of Thomson is a presentation of K-theory in terms of asymptotic homomorphism, namely homotopy classes of asymptotic homomorphisms, which are contractive and completely positive. Okay, so E-theory with completely positive maps, contractive completely positive maps, it's KK. Okay, so this illustrates neatly the difference between KK and E-theory. And what is the key fact that Thomson employs is that if we have an extension which is semi-split, this means there is an asymptotic homomorphism from A to B which splits the quotient map. And if this asymptotic homomorphism is completely positive and contractive, then the boundary map, the Cohn-Hickson homomorphism associated to this extension, which goes from the suspension of B to the ideal, can be represented, can be chosen to be completely positive. Okay, and this leads to homotopy equivalence between mapping cones and ideals through in this category of completely positive asymptotic homomorphisms. Right? Okay, so I will make a little interlude. So about Borsuk's shape theory. Okay, so I still want to emphasize this idea or discussion around the role of asymptotic homotopy. So Borsuk introduced shape theory in order to analyze spaces which may have local singularity or are very singular. And this should be at home in the theory of C-star algebras, because C-star algebras really can be very singular objects. So here I draw the so-called Warsaw circle, or a Warsaw circle, W1, and contrast it with the usual circle, and we have this like sine-like function, and this creates a singular side here. And these two spaces are not homotopy equivalent. The fundamental group of the Warsaw circle is 0. You cannot go through a continuous map around the Warsaw circle, whereas you can go around the circles. Okay, and then what Borsuk proposed was to consider germs of epsilon thickenings of such space. And I will indicate this by adding an epsilon subscript. Okay, so you are fattening this space. You take an epsilon neighborhood. And if you do this, it's apparent then this, for any epsilon, the thickening of these spaces, they become homotopy equivalent, because this singularity here is absorbed by the thickening. Okay, and Borsuk called these two spaces shape equivalent. So, and then shape theory was developed. Essentially, it's a homotopy, a coherent homotopy theory of these germs of epsilon thickenings. Okay, and what is the connection? What is the connection with asymptotic homotopy? So in the early 90s, I studied this, and then I showed that, in fact, that compact spaces or locally compact spaces are shape equivalent precisely when the corresponding commutative algebras are asymptotic homotopy. So shape theory has this very neat, well, I think it's neat description in terms of asymptotic homotopy using asymptotic homomorphisms. And okay, so, but once we introduce non-commutative object C-star algebra, such like the compacts, that changes dramatically the picture. This brings, well, something that a priori perhaps should have been unexpected, but not here. So what happens is that the suspension of the compact operators and the third suspension of the compacts, they are asymptotically homotopic. So you might say that these two C-star algebras have the same shape. If you allow for a natural notion of epsilon thickening, you soften the algebras, then a new phenomenon appears. So of course here is both periodicity, which in some sense it's something very much different than the issues of singularity. And one can formalize this thing in the following way. Of course, one might argue, what do I really mean by shape? So let me just say that one can recast these properties by saying that if f is any functor from separable C-star algebra to any category, a functor which is homotopy invariant, so we do not assume that this is an abelian category or a category of groups, but we assume that if we consider a direct system of C-star algebras, we assume that its image, of course, will be a direct system, and we want that to have limit if the initial direct system that we plug in has direct limit. So this means if we have a continuous functor, that any such functor cannot distinguish between the suspension of A stabilized and the suspension of A. So in this sense, in some sense, is justified. We are justifying saying that these algebras have the same shape. Well, anyway, so this is the second role played by asymptotic homotopy in KK theory. Okay, so now if I go back to Thomson's theorem, so of course, we all know about the canonical map between KK theory and E theory, and it has this elegant realization when you go from completely positive asymptotic homomorphism to asymptotic homomorphism. Of course, if the algebra A is nuclear, then all the extensions are semi-split, and then by Choi-Ross, this map is an isomorphism as a consequence of Choi-Ross and the discussion above. Okay, now having revisited all this, I want to discuss the question of unsuspending in E theory. So initially, when I look at this question, I was motivated by classification theorem, so of separable C-star algebras. So at the time we were studying various inductive limits, and we wanted a way to go from K theory to star homomorphism. And okay, but it's hard to produce star homomorphism out of K theory. And I said, okay, when E theory was discovered, I said, oh, we have a great way of going from KK to maps. Because E theory is just maps. Well, yes, but unfortunately, there are maps from the suspension of A to the suspension of B. Okay, and we really wanted maps from A to B. So then it's natural to inquire when it is possible to unsuspend in E theory. Right, so another question. In other words, the question is, we have a canonical maps from homotopy classes of asymptotic homomorphisms from A to B to the same algebras after we taking suspension to E theory. And the question is, are there interesting instances under which this map is an isomorphism for any C-star algebra B? For any C-star algebra B. And what are the obvious obstructions? So first of all, this is just might not be a group due to the compacts, present of the compacts. It's easy to see that this is a monoid, an abelian monoid, where the unit is 0. Okay, but in general, it's not a group. For instance, well, you can take A to be the complex numbers. Okay, so this is the minimum requirement that one must have. So this needs to be a group. And as it turns out, this is a condition. It's also not only necessary, but it's also sufficient. And this is what we proved with the learning. S is an isomorphism. We said if and only if A is homotopy symmetric. So the terminology, maybe it's unfortunate, but we were young at the time. So what do I mean by this? We have a canonical map from A to A tensor the compact operators once we fix an idempotent in K. And we ask that this map should have admit an inverse in this commutative monoid. In other words, if you add to this, I call it identity map, there should be some inverse, additive inverse. So identity plus some asymptotic homomorphisms should be homotopic. Well, through asymptotic homomorphisms, asymptotic homotopic to 0. Okay, and then if we can invert the identity in this way, then we call this homotopy symmetric. Okay, and one such an example that we pointed out at the time was that if X is a locally compact space such that one point compactification is connected, then you can unsuspend. Well, sorry. So the theorem is that you can unsuspend when the algebra is homotopy symmetric. And for such spaces locally compact with connected compactification, so C0x is homotopy symmetric. So therefore, one obtains this description of K homology of the space X as the homotopy classes of, I would like to call them deformations of C0x into the compacts. So here you can replace compacts by matrices, but then each phi sub t will land in a matrix of a different size. So informally, the deformation of C0x into matrices are exactly parameterized by the K homology of X. So this is one description of K homology, which comes from E-theory. Okay, and this is an interesting phenomenon, and in fact, I don't remember if I put it in the notes. In one of the mathematical model of topological insulator proposed by Kitaev, he connects this deformation of spaces. In fact, he just works with spheres into matrices, but this would be all the theory is over R to the theory of topological insulators. This is how he produces topological models for those. So I mentioned the formation of spaces, right? So for instance, in the case of a sphere, the equation of a sphere, if we write the equation of the sphere with matrices, self-adjoint matrices, maybe I should add here self-adjoint matrices, or we can assume that they are only asymptotically self-adjoint. Okay, now, so if we take self-adjoint matrices which almost commute, epsilon commute, and they epsilon add up to 1, and we ask, can you perturb those matrices to matrices which are commuting on the nodes? And the answer is no. Why? There is an obstruction in K homology of the sphere, so there is an obstruction in Z. The same thing with Voiculescu's examples, two almost commuting unitaries which cannot be perturbed to commuting unitaries. Why? Because the deformations of the two torus into matrices are parameterized by the K homology of the two torus, so fundamental cross. It's an obstruction. All right. So here I explain the connection. Then if the algebra is nuclear, then right, the deformation in the first place we get E-theory, but if the algebra is nuclear, as I mentioned, we get really K homology. So the question is, okay, so we have these commutative algebras, C0 of X. How to find other interesting classes? So an easy step is to take tensor products. That was nice, but still it's not sufficiently interesting. And then years later, together I revisited this question to get it together with Ulrich Penning. And then eventually we isolated this property. So we call a C-star algebra A, we call it connective, if it embeds in a corona algebra, where here is how this corona algebra is defined. We take bounded operators on a Hilbert space. We take the cone over the bounded operators, and then we take the infinite product. So this is the infinite product in the category of C-star algebras, and we divide it by the direct sum in the category of C-star algebras. So maybe this notation was direct sum. It's not precise, but this is direct sum in the suitable category. So one can write L infinity sequences with values in the cone divided by C0 sequences with vanish at infinity. All right, and okay, so sorry, what did I do here? All right, and now if the space X is path connected, then you can embed it. This algebra C0 of X, it is connective in the sense that I described. So maybe I'll just make one diagram here, one little drawing. So say that this is X, and this is the compactification X. And then if I consider any point X, I take a path, maybe gamma t, and then once I have this path, I can go from C of X to continuous functions on 0, 1. So I take f and I evaluate at gamma t. I compose with gamma t. Okay, and then if I take many, many points in the space X, well, it's separable, then the product of these maps will be injective, and therefore I get this embedding, which means this algebra is connective. So you can see that here path connectedness plays a role. But of course, lots of space are not path connected, are just connected. And in order to take care of that, one efficient way is to map the space not in a product of cones, but you are allowed some errors, okay, and that will correspond here that we don't take a continuous path, but only a path which is consists of small jumps. Okay, and anyway, so what is the role of connective algebra? So we showed with Ulrich that this is in the category for nuclear algebras, separable algebras. This is precisely the algebras for which one can unsuspend. So the way I formulated that A is homotopy symmetric if and only if A is connective. So this means that in this case, one can unsuspend. Okay, so it's not easy to understand this condition. Okay, but I will elaborate a little bit. But first, I would say that the nuclear connective algebras have some important permanence properties, direct limits, extensions, meaning that if the ideal and the quotient are nuclear and connective, then the extension in the middle is also connective, and then cross product by compact groups. So these permanence properties give lots of examples of connective system algebras for which therefore you can unsuspend in E-theory. Okay, and then we wanted to exhibit more examples related to classical objects, and so here it's a list of examples. Of course, if you look at Lie groups, linear connected complex semi-simple Lie groups, for such a group, the C-star algebra is connective if and only if G is non-compact. For real groups, linear connected real reductive Lie groups, the C-star algebra is connected if and only if G does not have a Cartan subgroup or there is no discrete series. What about discrete groups? The C-star algebra of a discrete group, has a unit. Okay, so if you have a unit, forget about unsuspending. But the way one handles this, one considers the augmentation ideal right? So it is this codimension one ideal in C star gamma. And then in this case, this turns out that this is connective. Okay, so maybe just to add intuition, right? So continuous functions. So let me take, if gamma is the integers, the C star algebra of gamma is continuous function on the torus. Of course, it's not connective. You cannot thus suspend due to the unit, but the augmentation ideal is continuous functions on a circle vanishing at a point. Okay, so now this was covered by what we discussed. So it is connective, and this holds more generally. So in general, if one looks for discrete groups, which might be connective, so one needs them to be torsion free, and then this is the object, the natural object to consider, documentation idea. Now, when we study this, we also observe that this condition depends only on the primitive spectrum. And what we showed is using Kirchberg theory that if A it's, I think was nuclear, and connective C star algebra, then the primitive ideal of A, which of course is non-Hausdorff in general, has no non-empty compact open subsets. Okay, so this reminds us of the definition of connected spaces, but this is non-Hausdorff. So this is why we propose this terminology of connective. You know, the primitive spectrum is not connected; it's connective. Okay, and then a truly remarkable theorem was proved by Jamie Gabe, namely that this condition is also sufficient. So a separable exact C star algebra is connective if and only if its primitive ideal contains no non-empty compact open subsets. All right, so maybe I will return to the theme of the talk again. Namely, let's contrast homotopy with asymptotic homotopy once more. So even if X and Y are finite connected CW complexes, so these are spaces whose structure it's very nice, it's the optimal local structure. Nevertheless, there is a huge difference between homotopy classes of star homomorphisms and asymptotic homotopy classes of star homomorphisms. Okay, so the issue here at hand is not possible local singularity of the space, but the role played by the compacts. Okay, so in one place with asymptotic homotopy, one obtains KK theory, whereas if one works with star homomorphism from C0 of X tensor the complex to C0 of Y tensor the complex. So in this case, I show that with Nemeti that one obtains a group, and then based on the work of Grimm-Siegel, we prove that this is an abelian group, and then if you take one of the variable to be 2 points, then you get connective K theory and connective K homology. But the theory does not extend well to C star algebra. But there is a connective version of KK for commutative algebras. Okay, so again, this highlights this contrast, homotopy, asymptotic homotopy. All right, and finally, the last topic that I want to touch upon, it's a duality isomorphism between KK theory and K theory. So we fix an absorbing representation of A into linear adjointable operators on HB. So I'm using here Kasparov's notation. And we take an absorbing representation of infinite multiplicity. Infinite multiplicity is that P is equivalent to an infinite multiple of itself. And what does it mean that it's absorbing is that any other representation is contained, well, wiki contained in this representation. And there are such representation. Thomson showed that for separable algebras, there are such representations using Stein-Spring theorem. Okay, and then inspired by work of Guoliang Yu, John Rowe, and Kiao, we introduced this local algebra associated to the representation, which is defined the following way. So we consider here functions. We consider functions from, remember, this T was the interval, the semi-interval. So we consider functions, f of t, with continuous functions in L of HB, and functions which are, okay, yeah, I need the correction here. They are bounded and uniformly continuous. Uniformly continuous. Okay, so let me adjust here. We want them to be uniformly continuous. All right. So see, these are like infinite paths into LHB. And then we consider those paths which commute asymptotically with the representation. And moreover, those paths, such that if we multiply them pointwise with representation, we land inside the compact operators. You see, the product is compact, and then they commute asymptotically. Since the extension is absorbing of infinite multiplicity, it only depends on A and B. So if I take another representation of this type, the corresponding algebras are isomorphic. They are intertwined, actually. The isomorphism is implemented by unitaries. So this is why one may refer at this localization algebra CL of A and B depends only ultimately up to isomorphism only on A and B. Okay. If you have not seen this before, might take a while to absorb it, but I'll just say this. If the algebra, if A is unital and if the representation is unital, then this condition that the product is compact, see if I take one here, then that simply means that F takes compact values. So see, in this case, we take infinite paths of compacts. Okay, such that these paths commute asymptotically with representation. So see, this localization algebra, it's the asymptotic commutant of A in these algebras of paths. So again, the key word is asymptotic. So again, asymptotic paths, asymptotic homotopy, seems to play a crucial role in KK theory. Okay, so now we have we have this algebra, localization algebra. And the result with Rufus, Willett, and Zhang Chao Wu is that there are canonical isomorphism between Kasparov groups and the K-theory groups of this localized algebra. And I want to emphasize that unlike the Paschke duality, there is no shift in dimension. And if one recalls Paschke duality, that also involves a commutant. So a commutant inside the Kalkin algebra. Okay, so this is also some sort of commutant. It's not Kalkin algebra, it's compact operators, but in fact, not just compact operator, pairs of compact operators. So this duality algebra must be non-separable, because K-homology of a separate algebra, in general, it's non-separable. It's not uncountable. So this is unavoidable. But this is a different model of the dual. Okay, and the proof it's technical, but I just want to make one point near the end of the talk. Yes. So let's assume that I take a projection. Okay, so P is a projection. It's not in K0. So assume I take a projection, okay, in this localization algebra. Okay, now if I compress the representation by the projection, okay, now what I get is a compact operator, because that was the condition, that the product is compact. Okay, and therefore what we obtain by compressing representation by P of t, we get an asymptotic homomorphism from A to the compacts. Right? But this gives, since this compression, it's a completely positive map, I get an asymptotic homomorphism of completely positive maps. Okay, and therefore an element of KK. Okay, so this gives you an idea indirectly why K0 of the localization algebra might have anything to do with KK. Okay, if projections are available. Okay, and why is it that Goliang Liu considered this algebra? The flavor is the same, but there are some technical aspects, because he wanted a description, a very accessible description of the pairing between K-theory and K-homology, which in general is complicated. Why? Because it involves head-on theory, okay? Computing pairings, even for manifolds, it's the content of Atiyah-Singer, right? So a sub-example of the previous example is that if I have a projection in localization algebra, and if a projection in A, if I multiply these two projections together, I get a compact operator, okay, which is, due to commutativity, it's a path of almost projection, which one can perturb to a path of projections, which of course must have constant rank, and this rank gives the integer. So this is the pairing, you see. You don't have a Fredholm index here, but you multiply two projections, and you get asymptotically a path of projections of constant rank, and that's the pairing. So this is how you localize the Fredholm index. So I would like to finish here, and thank you very much for listening.
Thank you very much for the talk. Let's thank the speaker. Any questions?
I have a question.
Yeah.
So I was just wondering if have you thought about the Kasparov product in this picture with these localization algebras?
Uh, there is a paper where certain aspects are studied, but I'm not sure if the Kasparov product itself, rather than just some pairings. I think it's Huao. She's at Shanghai. I think she and collaborators or something, but I don't recall exactly. So I don't know. That's the
Uli,
Okay, thank you.
yes, sir.
Uli, you're muted.
So you mentioned that the map from KK theory to E theory is an isomorphism if the first entry, the algebra A, is nuclear. And I mean, okay, in this Thomson picture, it's, I mean, somehow obvious. Yeah. And I mean, the other proof I know is complicated. I think it's by Skandales, about by constructing a nuclear, I mean, so the question is, do you have an easy argument somehow? I mean, or in this third picture, in this last picture, I mean, can you see this somehow? I mean, some easy argument why you get an ISO if you insert a nuclear algebra in the first entry?
Uh, yes, I will back. So in okay, so the question is why do we have an isomorphism for nuclear algebras? It's
So preferable, I mean, I want to see it using some universal property. So I want to see if the nuclear algebras have some property which implies this. I mean, not using the model. So, I mean, using the model of Thomson, for instance, okay, I see it.
well, I
But I
don't know.
mean,
Then I don't know any other explanation without the model. Yeah. But for me, the explanation. Look, so for me, I have this explanation, right? Why don't we have excision in singular cohomology, right? Because you have these spaces, subspaces Y, which might occupy a singular position inside X, right? The pair is not excisive, okay? Now, this condition that I have here on the slide, the existence of a completely positive splitting. In fact, I had in mind to mention this. This is a regularity condition for the pair. You know, we might say, okay, this pair is excisive if having uh, the subspace sitting nicely in the ambient space. Here in the realm of functional analysis, you ask they sit nicely in the sense that you have a splitting, a completely positive splitting. Okay. And then nuclear algebras by Choi-Efros, every surjection semi-splits. So in this sense, nuclear algebras can sit only nicely. I mean, all quotients sit nicely inside the ambient algebra. So that's my viewpoint. I mean, an explanation that satisfies myself. But I don't know if this uh, follows from general arguments, but KK needs this completely positive splitting because otherwise, right, the mapping cone is not equivalent to the ideal. Uh, right, but if you have this splitting, then it is equivalent to the ideal going through completely positive asymptotic homomorphisms. I apologize if I misunderstood your question. But,
I also have one question, namely with respect to this localization algebra and the equivalence to the KK groups. So is there mild generalization of this where you also involve tensor products such that it becomes the formula for an internal home?
You're
So
telling me that this has been generalized? Is this?
no, I'm not telling you, I'm asking whether this exists. So yeah. So the question is whether this localization algebra is actually an internal home in KK, meaning that you could tensorize, yeah, on the left-hand side also with a T, dA, and on the right-hand side would have KK groups from T to this localization algebra.
There is a paper that was mentioned by in the talk by Arthur by Goliang Yu and Rufus Willett, where I think they look at some functoriality property of the constructions, but I don't recall the details. But yes.
Thanks. Anyway, yeah. So let's maybe turn off the recording.